Cool. Sweet. So we'll start with a little bit of revision just to catch up on where we were at from last term. Cool. So what is the purpose of a circuit schematic diagram in electrical work, and how does it differ from a layout plan? All good, Sasha. Glad you could join us. So yeah, the purpose of a circuit schematic diagram in electrical work, and how it differs from a layout diagram. So a circuit schematic diagram shows the electrical connections and components in a symbolic form, focusing on the function of the circuit rather than physical locations. And a layout plan shows the physical placement of components in a building or an installation. Cool. So explain the difference between energized and de-energized in the context of contact position. Cool. Some good answers. So energized means power is supplied to a device like a relay or coil, causing it to change state. So example, the normally open contacts close and normally closed contacts open. De-energized means there's no power supplied and the device returns to its normal positions. So it's normal, non-energized state. Cool. So what does braking capacity mean? Okay, some interesting answers there. So breaking capacity, or we usually sometimes use the term rupturing capacity, is the maximum fault current that a protective device such as a circuit breaker or fuse can safely interrupt without damage or danger. It's typically expressed in kiloamperes, Ka, and ensures the device can handle high fault levels without catastrophic failure. So it's the maximum current you can pass through a fuse or a circuit breaker without it exploding, basically. So what is the difference between an MCB and an HRC fuse? Yeah, some good answers there. Cool. So an MCB or a miniature circuit breaker is resettable, electromechanical device that automatically switches off the circuit during overload or short circuit conditions. It combines thermal and magnetic protection and can be easily reset after tripping. An HRC, or high rupturing capacity fuse, is a single-use device that contains a fuse element inside a ceramic body filled with silica sand. It melts under fault conditions to interrupt the circuit and must be replaced after it operates. HRC fuses generally have a higher breaking capacity and are suited for industrial applications. Cool. So that's the revision portion for tonight. So tonight we are going to start talking about magnetism. So first things first, what is magnetism? What do you guys reckon magnetism is? Give a brief description or summation of what it's magic. I like that. Magic rocks. Yep. Yep, that's what we use magnetic fields because the way it interacts with electricity. Yep, electromagnetic field is a type of magnetic field. So we'll take a look at what it is. So definition is magnetism is a force caused by the motion of electric charges, resulting in attractive and repulsive forces between objects. So some everyday examples: fridge magnets, magnetic clasps, and magnetic compasses. Yep, that's a good point, Jack. Yep, we'll go into that a little bit later as well. Cool. So understanding magnetism is fundamental to electrical engineering, particularly in the design and function of motors, generators, transformers, and relays. Cool. So one of the things we need to look at when we're talking about magnets is domains. So has anyone heard of domain theory before? Okay, so we're going a little bit back to a little bit of high school physics and science. But basically, magnetic materials are made up of small regions called domains. Each domain acts like a tiny magnet with its own north and south pole. So in unmagnetized materials, the domains are randomly oriented and the magnetic fields cancel each other out. So we look at the screen, you've got the small little arrow, which is your domain. And so this is a demagnetized bar. So you can see the domains aren't lining up. They're all just kind of all random all over the place. But when it's exposed to an external magnetic field, the domains start to align in the direction of the field, creating a net magnetic effect. This process is what we call magnetization. So once they're aligned, the material becomes magnetized and can produce its own magnetic field. Some materials retain this alignment, permanent magnets, while others lose it when the external field is removed, temporary magnets. So we move from having an individual domain and domains that are all kind of random, and then they slowly, as we pass over the magnetizing field, they coalesce and they all line up like this. So that is how domain theory works. See there, they'll move around and then they line up and become magnetized. Cool. So magnetic materials are usually alloys of iron or steel. Uh, a bar magnetic material may be magnetized or it may display no magnetic properties whatsoever. The bar is assumed to consist of a large number of miniature magnets, domains like we were talking about. When they are pointing in any and all direction, it exhibits no magnetic properties, so it has not been magnetized yet. When they all line up, it is said to be magnetized. Cool. So when an external magnetic force is applied, the domains line up. As more and more domains line up, the magnetic field becomes stronger. Domains are fully aligned and the overall magnetic field cannot become any stronger. This point is called saturation. So in unmagnetized materials, the domains are randomly oriented and the fields cancel each other out. Cool. So types of magnets. So first type of magnet we'll talk about is the type of magnet the shepherds used to use many years ago, or a natural magnet, or a lodestone. These lodestones are found in nature as rocks and stones. They aren't usually of a great strength, so cannot be put to use commercially. The first type of magnet was a natural magnet. It would make sense that the other type would be artificial. Artificial magnets can be categorized into two groups. So natural magnets are basically they exhibit magnetic properties without any human intervention. What do you guys think the shepherds used to use the lodestones for? Or what do you think before we understood how to create more magnets? Yep, yep, you guys are on the right path. Yep. So they reckon that the shepherds and also the Vikings used to use lodestones to create compasses, and that's how they were able to sail. Know they were sailing in the right direction to sail to England during the Viking Age. Just random facts. Cool. So Permanent magnet. So a permanent magnet will retain its magnetic properties once the external force that magnetize it is removed. These magnets are often hard materials and require a reasonable amount of force to magnetize. Once they are magnetized, that magnetic property will stay with it for a great deal of time. So man-made magnets are created by humans through magnetizing ferromagnetic materials such as iron or steel, or by engineering alloys and composite materials like alnico or rare earth magnets. So neodymium magnets is an example. These are specifically designed to produce strong and durable magnetic fields. Um, so what do you guys think the term ferrous means? On the right track there, Timothy. Yeah. So when we talk about ferrous or Fe materials, so ferrous is the Latin or Greek, I can't remember which, name for iron. If you look at the periodic table, you'll see that iron is represented by the term Fe. And because iron is the first material that they found to be able to be magnetized and stay magnetized, they deemed that any material that could become magnetic is a ferrous material. Can someone give me an example of a material, a metal that is non-ferrous? Yep. So some examples of non-ferrous metals. You've got uh, aluminium, copper is technically non-ferrous. Yep. Zinc, lead, nickel, titanium, and precious metals like gold and silver. They are known for malleability, corrosion resistance, and high electrical and thermal conductivity, but not very good for magnetism. Cool. And then we move on to temporary magnets. So a temporary magnet is a material that can be magnetized by an external force and retain the magnetic property so long as the external force continues to act upon it. Once the external force is removed, they do not take long to lose their magnetism. We'll discuss some key terms around these concepts shortly. They are essentially a magnet created by the use of current flow. We can create a simple electromagnetic by wrapping a piece of insulated copper wire around a nail and applying a current. So they're a man-made magnet created by running electric current through a coil of wire, often wrapped around an iron core. They produce a magnetic field only when the current is present. Yeah, someone give me examples of where we use electromagnets on a day-to-day basis. Yeah, motors are technically a form of electromagnet. Can someone think of some others? Yeah, relay, door locks. Yep, contactors, tools. Yep, some tools, doors. Yep, generators are. Yep, they use electromagnetism to operate. Box. Yeah. What about a really big electromagnet? What would you use that for? Yep, an MRI is a good one. Yep, scrapyard. Scrapyard. Yep. Solenoids. Yep. Transformer is it works on the basis of electromagnetism, and it only works when we put current through it. Yep. You'll have to explain what a DSG gearbox is, Jack. Not familiar with what a DSG is. Is that diesel standby generator? Vita. Oh. Okay, guys, cool. Cool. So not everything can become a magnet. So materials that can become magnetic as the nature are called ferromagnetic, like we talked about. An example is iron. So any material that contains iron has the ability to become magnetized. There is a large lump of iron underneath northern Canada that forms what we know as magnetic north. And if a bar of magnetized metal is suspended, this is where it will point and is the principle of how a compass works. So what do you think one of the big risks of there being a giant lump of iron underneath northern Canada? What do you think one of the risks of it being there is, especially as we live in an age where we need more and more metal? Yeah, exploitation. Yeah, what's the like? So what would happen if we were to mine that iron and reduce its mass? Yeah, no true north. Yeah, lose polarity. So what would happen if we I don't know about protection from the UV rays because I don't think that's dependent on the magnetic field, but what might happen to the way the world spins? Yep, might slow down. It might change its axis. Will it stop? I don't know about stop because there is a massive so there's a giant chunk of iron, but there's also the Earth's core, which is highly magnetic as well. To be truth, we don't know, but I'm pretty sure there is an agreement between Canada and the rest of the world that they're not going to take too much, but you never know. Giant electromagnetic. Yep, sweet. Problem solved. Cool. So now we'll talk about magnetic saturation. What do you guys think magnetic saturation means? Give me a short description of what it means. I'm liking the answers you guys are putting forward. Cool. So magnetic saturation occurs when an increase in the external magnetic field cannot further increase the alignment of domains within the material. So like we talked about before, it's when all of the domains are lined up in one direction and there's no more domains to change. It's the full magnetic saturation or it's completely magnetized. It cannot be magnetized any further. So at this point, the material has reached maximum magnetic flux density, which we'll talk about flux density later, and additional magnetizing force will not result in a stronger magnetic field. So understanding saturation is important for designing electromagnets and electrical machines as it sets a limit on their efficiency and their effectiveness. So imagine these domains like little iron filings pointing in all different directions. When we magnetize a material, it's like lining them all up to point the same way. But once they're all lined up, no matter how much harder you try, they can't point any straighter. That's saturation. Cool. And now we'll talk about reluctance. So reluctance, similar to resistance, is the opposition to the setting up of flux in a magnetic circuit. It can be likened to resistance in an electrical circuit. So the magnetic flux will endeavor to travel through the path of least resistance, or reluctance, sorry, when completing its circuit from the North Pole to the South Pole. So the magnetic field within the magnet always goes from north to south. This can mean traveling a little further physically if it means an easier path through a material, that has less reluctance. So is this making sense, the idea of reluctance? Yeah, so one way to think about it is you've got very a not very reluctant material bent over a more reluctant material. So an iron bar bent around, say, a aluminium former. So that magnetism is going to go all the way around the aluminium former because, or say the copper windings, because it can't go into the copper winding, it's going to want to travel through the iron around the outside instead. Cool. And then we talk about magnetic screening. So magnetic screening is a process in which magnetic flux is diverted around something by using a material that flux would rather travel through. For example, sensitive electronic equipment can be adversely affected by magnetic fields. To remove this, we offer a path of lower reluctance for the magnetic flux and put it around the equipment we're trying to protect. So you can give me an example of where you might need magnetic screening or a type of magnetic screening. Microwave, yep. Protect the radiation from getting outside, yep. Yep, lead line for jib x-rays, yep. Or lead lined around the MRI, yep. Yep, that's a good one. Sheathed cable for a VSD, yep. Yep, Faraday cages, that's a good one. Yep. So the idea behind a Faraday cage is that it will protect against radiation or magnetic rays. There are a lot of survivalists and doomsday preppers who, yep, Cat 6 is sometimes shielded. So they are buying these Faraday cage bags or Faraday cages and putting in electronic equipment inside the Faraday bag and then inside another Faraday bag because they believe at one point a solar flare will be Faraday box for your 5G router so you don't catch COVID. Yep. Yeah, so they put them in these Faraday bags to protect them against what they think is going to happen, which is mass solar flares, which are going to create solar waves across the planet. And basically, their thinking is that the wave is going to be so powerful that it's going to induce a whole bunch of EMF into our networks and power distribution to the point where it will melt all of the power lines. Um, it is a bit of a crazy theory, but it's not the craziest one I've ever heard. Yes, I'm inclined to agree with you on that one, Tim. Yeah, that's going to be the least of our concerns. Um, yeah, because all of the copper will have vaporized. So how are we supposed to rebuild? Cool. So moving on from that lovely topic. So relative permeability. So you have a look at the two electromagnet magnets below. So one would assume that each coil being made the same, that the strength of each magnet would be the same. This is in fact not the case. The core that is in the middle makes a huge difference to the strength of the magnet, in the sense that the coil with the iron core makes it much stronger than the coil with a wooden core. This is because the iron is a magnetic material and has a higher relative permeability than the wood, which is non-magnetic. So relative permeability is essentially a multiplying factor that affects how much greater the magnetic strength of the coil will be. So we talked about reluctance, which is the opposition to the setting up of a flux in a magnetic circuit, and then permeability or relative permeability. So relatively speaking, so wood is less permeable than iron, but one iron core might be more permeable than another iron core, but they have the same reluctance. Cool. And then we talk about a magnetic field. So, an area around a magnetic material or a moving electric charge within which the force of magnetism acts. So, magnetic fields are represented by lines of force that emerge from both the North Pole and enter the South Pole. So, they come out of the North Pole and enter the South Pole. This field indicates both the direction and the strength of magnetic influence. The closer the lines, the stronger the field. So if we go back to looking at that diagram, the closer the lines are, the stronger the field, or the more lines, the stronger. Okay, that's actually rather, sorry about that. Cool, lines of force. Imaginary lines that represent the direction of magnetic field. So they form closed loops. We'll have a look at this in a little bit. From the north to the south pole, outside the magnet, and continue from south to north, inside the magnet. That's how wide the field is, but field strength is about density. So we'll look at it in a little bit. Cool. So magnetic poles and polarity. So it refers to the two distinct regions of a magnet where the magnetic forces are strongest. So north and south poles. And like most of us know, like poles repel each other while opposite poles attract. Cool. So the Earth's North Pole. So geographic North Pole. This lies in the central part of the Arctic Ocean and is the point of intercrossing of all meridians and time zones of our planet. So it's the geographic North Pole. The North Magnetic Pole is the conventional point where the Earth's magnetic field is oriented to the planet's surface at a right angle. The position of the magnetic North Pole is not set and is not easy to locate because it constantly moves on the elliptic trajectory of the north and northwest. Since the second half of the 20th century, the magnetic North Pole moves towards the Taimyr Peninsula with the annual speed of 1 kilometer up to 10 kilometers in the years of high geothermal activity. So the North Magnetic Pole is constantly shifting, whereas the geographic North Pole is central part of the Arctic Ocean. Cool. So the third one is the place which is colder than the North Pole. So if we look at the meteorological maps, it can be found under the name Pole of Cold. It is situated in the Yakut settlement of the Oymyakon in East Siberia. This is not stuff you need to know too much about. Of course, so during winter, the temperature here can drop as low as -50 or -60 degrees Celsius. The absolute minimum here was registered in 1993 at -67.7 degrees. Oh, that sounds cold. It's the coldest place on Earth where people live in such unwelcome conditions on a constant basis. Good luck to them. I would not live there. Cool. So the fourth pole, North Pole of inaccessibility. It is the most remote point of the Arctic. It's situated as far from the mainland as possible, and it's situated on the 170th meridian of the eastern longitude and almost 600 kilometers from the geographical North Pole. Because this place is situated that far, it is considered to be mostly inaccessible. So this is stuff that's cool to know, but you guys don't need to worry about it. Cool. So magnets. Cool. So we've all seen basic bar magnets. We've seen the cartoons where they are lined up south, north, north, south. Cool. So attraction. So we know opposite poles attract. So north is attracted to south, south attracted to north because they are opposites. And then like poles, repulsion. They repel each other. Because they're alike, they repel each other. Cool. So magnetic field. So a magnetic field is a name given to a region around a magnet where its magnetic effect can be detected. So the field is where we can detect any form of magnetism, and it's usually a given area. So the lines dictate how strong the field is. So we can see here those lines where they are at. If we were to shrink them close together or add more lines, we would be increasing the field strength. Cool. So this can be done using a compass, another magnet, or a piece of magnetic material such as iron or steel. Cool. So magnetic fields. So the diagram shows the field lines between bar magnets, which are attracting, and those which are repelling. So we look at the opposite poles. So you see the magnetic lines are wanting to go from north to south. And then so we push the magnets that have a north and south close together. The lines that were going around the bar magnet are now going to line up and go towards each other and pull them apart. And the like poles down the bottom repel each other. So if you can see, the magnetic lines are both trying to come out of the North Pole. And so as they come out of the North Pole towards the other North Pole, they hit each other and deflect. That deflection force, or as we try to push it together, is what's stopping us from pushing those magnets together. So field patterns. So they're the invisible lines of magnetic flux. They can be rendered visible by sprinkling iron filings over the magnet. So the following sketches illustrate the field patterns which can be seen using this method. The flat paper can allow only a two-dimensional view. In reality, the lines occupy a three-dimensional space. So just because we see it here in 2D, it is actually in 3D. Bear with me 1 second. Cool. So you can see the bar magnet, and you can see the way that as I move the bar magnet, all of these compasses move. If I take the compass and I move it right next to the bar magnet, you can see it's going from north to south. But if I move it down here, the needle moves and points towards the south. So the white is pointing towards north, but the red is pointing to south. Then if we flip the polarity, compass flips the other way. And there we can see inside the magnet, they're doing the opposite. So the red comes this way, wants to go in, and then come out the other side. And then here, this is the field meter. If we move it closer, we can see all of the numbers change. So it's measuring the strength of it. Turn that off. Here, we can see a pickup coil. So as we move the magnet through, we can see it generates an electric charge, but only as the magnet is moving. So once the moving stops, the light stops. Oh, and we can change it to a voltage, and we can see here we get a negative and then a positive, a negative and then a positive as we move it through. If I move it through really quick, you can see the meter jumps quite quickly. If I move it too fast, you can't see. Cool. Here we can see an electromagnet. See how the electromagnet affects the compass and the magnetic flux lines around it. So you can see the electrons moving. Oh, I'll take that away. And then if I decrease the voltage and reverse, you can see that the compass lines go the other way. But as I decrease the voltage, you can see how weak the magnetic effect is by how bright the compasses are. And if I get to zero, there's nothing. Cool. So here you've got a transformer. So we've got a battery here, and if we move it through the coil, the light comes on. And then if we move it to a voltage indicator, I slowly move it through. You can see the voltage goes one way and then the other. And here we have a generator. Cool. So as I open the tap, it begins to spin. See the voltage going into positive and then negative and then negative, positive as the magnet spins. Cool. Just a handy little demonstration there. Cool. So field patterns. So magnetic field lines of a bar magnet in A. You got the magnetic lines between unlike poles in B. You can see they again try to go from the north to the south. And then magnetic field lines between like poles. So there's no EMF when the magnet is not moving because there is no change in the basically the magnetic field. If it's not moving, it's not cutting across and therefore not inducing a voltage. So if the magnet sits still inside the coil, there's no change in magnetic field. It's the change in magnetic field that induces the EMF. So only as we alternate or change the field is when the voltage is induced, which is why how generators work is that they're constantly moving to generate an EMF. If the generator is not moving, then the magnet's just sitting there. It's not creating a alternating field. It's not, if there's no movement in the field, there's nothing for the electrons to chase. And if the electrons don't have anything to chase, they're not going to move. So that's how the EMF is generated through the changing of the magnetic field. So if there's no changing magnetic field, we don't get an EMF. Does that make sense, Sean? Sweet. Awesome. So direction. So drawn opposite is the schematic field pattern for two bar magnets lying parallel to each other with adjacent north and south poles. So if you look at the location of point X, it's a point of zero magnetism. Because all of the magnetism is wanting to flow to the north and south poles, they're essentially ignoring that middle section. But obviously, if we were to lie two bar magnets next to each other like this, unless we were to put something in between them, they would just snap together, closing that area of no magnetism. Cool. So the properties of the flux lines. So they have the following properties. So they always form closed loops. Flux lines leave the North Pole and then enter the South Pole. Flux lines flow from north to south externally and from south to north internally. Adjacent lines repel, so flux lines never touch each other. And flux lines never cross over each other either. So if you ever ask to draw them, you make sure they never cross. So these properties explain why poles repel, like poles repel, and unlike poles attract. And then we get into the inverse square law. So the force of attraction or repulsion between two poles of a magnet depends on the strength of each pole and the distance between the two. As the distance between the two poles is reduced, the force between the poles is increased. It can be expressed in the following formula. F equals m1 times m2 divided by d2, d squared. Cool. So we'll have a look. So the following equation to see how the relationship works. If the strength of each pole is 1 and the distance is halved from 1 to 0.5, see how the force increases by 4 times. So F equals m1 times m2 divided by d squared. So the force is equal to 1 times 1 divided by 1 squared. So 1 divided by 1 equals 1 Newton. Cool. So F equals m1 times m2 divided by d squared. So same equation, but so 1 times 1 divided by 0.5 squared, which actually ends up being 0.25. So a force of 4 newtons. So that is the force of either attraction or repulsion, depending on what way the magnets are facing. Anyone confused by how the equation works? Everyone get it? Cool. So I will be sending you guys via a Google Drive link at the end of the lesson a worksheet that will have some of these equations. So we'll go over that next week, but it'll be some homework for you guys. But for now, all you need to know is the force of repulsion or attraction is equal to the field strength of m1, m2 divided by the distance between them squared. Cool. Magnetizing force. Cool. So a magnetizing force, H, so as expressed in Henry's, is directly proportional to both the current through the coil and the number of turns, N, so which make up the coil. And it's inversely proportional to the length of the magnetic path of metal core, which in this case is the length of the coil. Cool. So the unit of measurement is often quoted as the ampere turn per meter, ATM to the minus squared, but because the turn T is not an approved term, more correctly it is the ampere per meter, AM. Cool. And the equation is H equals Ni divided by L. So the number of turns times the current divided by the length of the coil. So we'll put this into an example. Cool. So calculate the magnetizing force generated when a current of 50 milliamps flows through a coil, which has 1800 turns and a length of 3 centimeters. So remember to convert from centimeters to meters. So I will give you the equation and I want you guys to give it a go. So get out your calculators and give this one a go. getting some different answers. A little bit of consensus. So when we write out the equation, it becomes H equals 1800 times 50 times 10 to the minus 3. So we have to do 10 to the minus 50 times 10 to the minus 3 because it's 50 milliamps. So we need to convert the milliamps into amps. So we need to times it by 10 to the minus 3 to move the decimal point 3 places. And 3 times 10 to the minus 2 because there are 100 centimeters in a meter. So we need to move the decimal place twice. And so that becomes 3,008 amp meters to the minus 1. So remember when we talk about magnetizing force, we're talking about amp meters. So H equals AM to the minus 1. So 3,000. Cool. So we will try again. So different rearranging of the formula. So calculate the length of a magnetic path of a coil of 1,250 turns generates a magnetizing force of 250 amp meters when passing a current of 35 milliamps. Cool. So we know that H equals Ni to the L. Therefore, L is equal to Ni divided by H. Remember, we need to convert the milliamps into amps, so times 10 to the minus 3. On your calculator, you will go 35 times, and there's a button down there next to the answer button. It says 10 times 10 to the x. So push that button, and then you use the negative button, which is on the left-hand side. In some brackets, you put negative, and then 3. So the length you should have ended up with is, or the calculation. For the calculator, so you take your 35 milliamps, and there is a button at the bottom next to the answer button that says times 10 to the x. Push that, and then there's a negative button halfway up on the left. It's the third one down, and then you put 3, and that'll give you the value in amps. Cool. So you should have ended up with a calculation like this: 1250 times 35 times 10 to the minus 3. So that 35 is times 10 to the minus 3 divided by 250 because we don't change the amp meters. And so the length is equal to 0.175 meters or 17.5 centimeters. So that is the value we get. Now we'll change the formula slightly again. So we'll calculate the current flowing in a coil of 1,425 turns if it generates a magnetizing force of 36 amp meters over a magnetic path of 9.7 centimeters. Cool. So we know H equals Ni divided by L. Therefore, I equals HL divided by N. So we'll go through the equation. So I is equal to 36 times 9.7 times 10 to the minus 2, because we need to change it from 9.7 centimeters to 0.097 meters, divided by 1425, which is the number of turns. So we get 0.00245 amps or 2.45 milliamps. Cool. So another one. So we'll calculate the number of turns in a coil when a magnetizing force of 2000 amp meters is generated when a current of 50 milliamps flows through a coil of length 3 centimeters. So remember to convert the centimeters to meters. Cool. So we take the formula H equals Ni divided by L, and we convert it to N equals HL divided by I. Yeah, as we'll go through it now. So the number of turns is equal to 2000 times 3 times 10 to the minus 2. Just remember to put that times 3 times 10 to the that 3 times 10 to the minus 2 in brackets, and then 50 times 10 to the negative 3. So the 3 we need to change from centimeters to meters, so we move the decimal place, so it becomes 0.03 meters. And then 50 times 10 to the minus 3 becomes 0.005, so amps, which gives us 1200 turns. So I think you didn't move the decimal place correctly, Sasha. I think that's why you got that 12 million turns, because the decimal place in the 3 and the 50 didn't get moved. Okay, possibly. Um, So we'll move on from this, and then we'll talk about magnetic flux. So when we talk about magnetic flux, they're the imaginary lines of magnetic flux leave one pole N and re-enter the magnet at the other pole S. The lines of flux do not touch or cross over each other. The total number of lines or amount of flux is taken as the value of magnetic flux, which is given with the symbol for Greek letter phi, and the unit of magnetic flux is the Weber, WB. So 1 Weber equals 100 million lines of magnetic flux. So it's a lot. So the flux tells us little about the distribution of the magnetic field. For instance, it is reasonable to expect the amount of flux in a given area close to a magnet to be greater than the flux in the same size area some distance away. So the magnetic flux is greater the closer you get to the magnet. Cool. And then we talk about magnetic flux density, B, which is measured in Teslas. So it's the concentration or density of flux passing through a given cross-section area of the magnetic field is called the magnetic flux density, symbol B, and is measured in Teslas, T. This can be illustrated as shown below. Cool. So magnetic flux density, by definition, the flux density within an area in A in meters squared of a uniform magnetic field is given by, so the flux density is equal to the magnetic field in Webers and the cross-sectional area of the magnetic circuit in meters squared. So B equals phi divided by A, the area. So prefixes and units, so magnetic flux, symbol phi, unit Weber, unit symbol WB. Flux density, symbol B, unit is Teslas, and the unit symbol is a T. Cool. And so when we're converting square centimeters and millimeters to meter, so magnetic flux density is measured in square meters, but few electrical devices are as big as this. Most are in square centimeters or square millimeters. The table below shows how to convert from centimeters and millimeters squared to meters squared. So from centimeter or square centimeters, it's times 10 to the minus 4. So we move the decimal place, it's times 0.0001. And the millimeter is times 10 to the negative 6. That's millimeter squared. So milli, or just m without the squared, is times 10 to the minus 3, and micro times 10 to the minus 6. That's for Webers and Teslas. So why do you guys think when we do centimeters squared, we times 10 to the minus 4? Yeah, basically it's squared, yeah. And then basically when you talk about exponents, you multiply them together. So because it's already squared, we multiply that squared and the -3 together. And so that's why we get -6 for millimeter. Cool. So we'll put this into an example. So we'll go through them and we'll just go through them because I see it's getting a bit late. Cool. So the magnetic flux at the pole face of a magnet is 0.2 MWB. So milliwebers, I'm pretty sure that's meant to be. And the area of the pole face is 0.02 meters squared. So find the average flux density at the pole face. So we use our calculation, B equals phi over A, or magnetic flux divided by area. So 0.2 times 10 to the -3, because it's milliwebers, it's meant to be a small m, but for some reason it's all capitalized. And the area of the pole face is 0.02 meters squared, so we don't need to change that. It just is 0.02. So B is equal to 0.01 teslas, or 10 milliteslas. Cool. So we'll rearrange the formula a bit. So to find the total flux requires on a magnetic pole face, which is an area of 80 centimeters squared, if the flux density is 0.4 teslas. So we take B equals phi over A, and there we go. Phi is equal to B times A. Cool. Which is equal to 0.4 times 80 times 10 to the -4, because we're in square centimeters, we need to do 10 to the -4, which gives us 0.0032 webers, or 3.2 milliwebers. Is this all making sense? Basically, with this calculation, we're trying to um, calculate yeah, it's all a lot of strange terms. So the original source material, no, it's not often used. This is kind of if you get into the transformer or solenoid development. Pretty much once you've finished with these units and these calculations, it will become yeah, I don't even think it will come up in your theory exam, but it is part of a unit that is required for you to pass in order to get your qualification, and therefore we are required to teach it. Oh, cool. Yeah. So again, this is being recorded. It's going to go on YouTube, so you can watch it again and follow along, and then pause it, slow it down, especially if these calculations come up in your assessments. They may or may not. So we'll go through one more example and I'll go slow. Cool. So the flux of 500 milliwebers coming out of a pole face gives rise to a flux density of 250 milliteslas. So we'll calculate the area of the pole face based on these values. So we know B equals phi over area. So therefore, area is equal to phi over B. Because we know from the original calculation, if we multiply phi divided by A and then move it to the other side, because we have to multiply both sides, we get A times B equals phi, but we need to find A. So we can then divide both sides by B. That's how we get this formula. So the area is equal to 500 times 10 to the minus 6, because when we're talking about phi, it's in milliteslas. And then 250 times 10 to the minus 3. So we get an area of 2 times 10 to the minus 3 meters squared, or 20 centimeters squared.